Welcome to this explainer. Today, we're pulling back the curtain on something massive. While the sweeping expanse of the ocean might just look like empty, open water to us, it's actually the stage for this unseen, brilliant daily choreography. We're talking colossal ships, incredibly intricate logistics, and high-stakes maneuvering. We are going to show you exactly how this awe-inspiring global engine really operates. Okay, let's dive into this by looking at the sheer, jaw-dropping scale of the operation. Picture a literal mountain of earth and rock. In modern ports, highly sophisticated loading systems can drop raw materials from great heights, packing over 200,000 tons of iron ore into a single ship, and they do it at blinding speeds. We're talking loading and discharging rates approaching 50,000 tons a single day. This isn't just moving dirt, right? This is feeding a voracious global economy that demands raw materials at breakneck speeds just to keep our industries alive. Section 1. The lifeblood of global trade. Before we meet the massive ships themselves, we really need to understand the vital resources they carry. So what exactly is moving out there across the oceans? Well, the big three by volume are iron ore, coal, and grains. But the list expands way beyond that, to sugar, forest products, fertilizers, steels, and minerals like bauxite. These bulk items are the literal lifeblood of global food supplies and steel industries. And as industrial nations grow, their soaring ton-per-mile demands dictate exactly where and how fast these commodities have to move. Let's ground this massive global scale into a really relatable detail. Take one surprising commodity, cassava. You probably know it as tapioca. But beyond being a pudding, it's this prolific tropical plant that gets heavily exported from Thailand all the way to the European Union. Why? Because European animal feed compounders use it as a cheap protein and energy substitute for more expensive, locally grown grains to feed their cattle and pigs. It just goes to show how intricately connected our global food chain really is. Section 2. Giants of the Ocean. Now let's transition to the cast of characters in our story, the colossal, brilliantly engineered vessels that actually move these mountains. Now, what's really interesting about this slide is the sheer contrast in engineering strategy. On one side, you've got the massive Cape-size vessels, ranging from 100,000 to 200,000 deadweight tons. These deepwater giants focus purely on hauling long-haul iron ore and coal. But on the other side, you have the highly versatile handy-size vessels. Clocking in at 20,000 to 55,000 tons, these agile ships actually have their own deck cranes, meaning they can go almost anywhere, navigating tight spots like the Great Lakes to deliver steel, scrap, and agricultural products. And sitting right smack in the middle, we have the Panamax ships. These are the absolute, undeniable workhorses of the sea. Ranging from 60,000 to 80,000 deadweight tons, they absolutely dominate those big three trades of coal, iron ore, and grain. Because they're the standard for so many major routes, like running grain from the US Gulf to Japan, their rates are basically the barometer for the entire shipping world, driving the highly volatile freight futures market. Now, to make sure absolutely no space goes to waste, operators use a brilliant tactic called the parceling technique. This is super common on handy-size and tween-decker ships, which basically act like the multi-tools of the ocean. Instead of loading one giant single cargo, these ships sweep up diverse cargoes. They'll load varied commodities into adjacent holds from multiple nearby ports before sailing off to their destination. It's an incredibly efficient way to maximize profitability. Section 3. Navigating a complex world. Let's shift our focus to the high-stakes obstacle course these vessels have to conquer. So what actually stands in the way of these ocean giants? Because the ocean isn't just open, unbothered water. It is this complex, invisible web of geopolitical borders, extreme weather events, strict union rules, and totally unforgiving geography. Let's start with geography. Ships constantly have to pass through legendary, thrilling navigational choke points, places like the Panamas, Suez Canals, the Magellan Straits, and the treacherous Cape Horn. These are massive logistical hurdles. A ship's every single move is dictated by things like whether ice will block the Great Lakes, if monsoons are going to strike, or how passing through different load line zones legally changes how much cargo they can even carry. Then, of course, there's the human element. International relations and union regulations can entirely reroute or delay a voyage. For example, charter parties often have to include clauses ensuring a vessel isn't boycotted by Arab nations due to past visits to Israel. Or if you're trading with Libya, you need costly Arabic translations of all your ship's documents. And in places like Australasia and Scandinavia, strict union rules require cargo hold ladders to have resting platforms every 6 meters. If your ship doesn't meet those standards, you simply aren't working. And this brilliantly illustrates the wild financial landmines hidden in this world. Look at this cost comparison for the exact same Panamax bulk carrier. A stop in Lisbon might run you about $15,000. Rotterdam jumps up to $60,000. But heading to Helsinki, that will cost a staggering $170,000. The stakes vary so wildly from port to port that charterers literally have to calculate their grand plan like a bank heist before they commit. Section 4, the precision of logistics. For our final act, let's zoom all the way down to the micro-level physics and math. Okay, this part is wild. Have you ever thought about the bizarre time-traveling reality of Pacific trading? When a ship crosses the international date line at the 180-degree meridian, the date changes instantly. If you sail east from Japan toward America, your ship literally gains a day. Sail west from America, and you lose a day. So when charterers are calculating exact delivery schedules, they literally have to factor in this chronological jump. So the crucial point is, how does the law handle this time-shifting puzzle when thousands of dollars are on the line? Say you're renting a ship for $9,000 a day. If you use local time, those time zone shifts could unfairly add or subtract hours, costing either the owner or the charterer a ton of money. That is exactly why English law favors the continuous, elapsed time method. It's basically a legal stopwatch that runs uninterrupted from delivery to redelivery, completely ignoring time zones to make things fair. Let's tackle one final, high-stakes math problem. How on earth do you fit a massive, heavily loaded ship into a shallow, freshwater canal like the Panama Canal? Because remember, ships actually sit deeper in less buoyant freshwater than they do in saltwater. This is where the ship's captain pulls off a precise lock-picking maneuver known as the salinity calculation. First, you pull the ship-specific freshwater allowance from its capacity plan. Second, you measure the exact density of the brackish, mixed water right there at the port. Finally, you run the formula. Multiply the allowance by the difference in water density and divide by 25. This isn't just dry math. This is a vital, real-world calculation to keep that ship from scraping the ocean floor. And here is the incredible results of all that math. Let's say a ship has a 200-millimeter freshwater allowance and enters slightly brackish water. That complex formula results in a draft change of exactly 80 millimeters. 80 millimeters! That is a staggeringly tiny margin when we're talking about ocean giants carrying hundreds of thousands of tons. But it literally means the absolute difference between a successful delivery and a totally grounded ship. So I have to ask, next time you see a steel beam holding up a building, a loaf of bread on your table, or just a bag of sugar in your pantry, will you think of the unseen, grand, cinematic, global engine that brought it to you? From the roaring 200,000-ton loaders down to an 80-millimeter salinity calculation, this beautifully complex system is literally what makes modern life possible. Thank you so much for joining me on this explainer, and keep wondering about the incredible world around us.